Welcome back. In this video, we're going to continue our lecture on lexical analysis with some examples from past programming languages where interesting lexical problems arose. So we've already talked a little bit about Fortran, and one of the interesting lexical rules in Fortran is that whitespace is insignificant. So whitespace doesn't matter, and something like var1, which could be a variable name var1, is exactly the same as VA space R1. So these two program fragments have to mean exactly the same thing. And the idea in Fortran is that you could take your program and you could delete all the blanks from it, and that shouldn't change what the program means at all. Let's take a look at an example of how Fortran's whitespace rule affects lexical analysis. Here are a couple of Fortran code fragments, and I should say that this example is taken from the Dragon book. And actually, a couple of the later examples are also taken from an older edition of the Dragon book. But anyway, what we have here, this is actually the header of a Fortran loop. And you know it's a loop because it has the keyword do, which is like for in modern C or C++. So that's a loop keyword. And then we have our iteration variable I, and we have a range that I will vary between. So in this case, I will go from 1 up to 25. And then this number 5 here, this is a little bit odd and something you don't see in modern languages. In the old days, in Fortran, you would have your do statement at the top of the loop, and then the size of the loop, or all the statements included in the loop, were named by a label that came right after the do statement. So the loop would extend from the header, the do statement, down to the label 5. So whatever statement was labeled with 5, all the statements in between would be part of the loop. And so the loop would execute those statements, then would go back around to the header, and it would keep executing those until it had done so for every one of the values of the iteration variable, in this case 1 to 25. Now here's another code fragment, and as you can see, this one is almost exactly the same as the one above. The only difference is, and let me switch colors, is here that this particular fragment has a comma in that position, and this fragment has a period. And it turns out that this difference makes all the difference, that these two fragments of code mean completely different things. So this fragment, the first one, is in fact a do loop, as I said before. So it has the keyword do, the label 5, the variable I, and the range 1 to 25. Now this fragment down here, this is actually a variable name, do5i. So if I was to write it without the blanks, remember the blanks don't matter, this would be do5i, and then this is an assignment equals the number 1.25. Okay? And so you can see here, these symbols, this first sequence of symbols is interpreted completely differently depending on whether there's a period or a comma further on. And so let's just be a little more precise about that. How do we know what do is? So let's just focus on the keyword here, do. And when we're at this point, when our focus is here, right after the O, and keep in mind that that the way this is going to be implemented is by a left to right scan. So we're going to be walking in this direction over the input, looking at each character successfully. And when our focus reaches this point, we can make a decision. Is this a keyword? Because we've seen the entire keyword do. And the problem is that we don't have enough information to make that decision. We don't know whether this is do or whether it's going to eventually be part of a variable name like do5i. And the only way to know is to look ahead in the input to this position to see whether there's a comma or a period there. So this is an example of lexical analysis that requires look ahead. In order to understand the role of do, as we're going left to right, we have to peek ahead in the input to see some symbols that come later on. And we can't possibly disambiguate the role of do until that point, because up to this point, the sequences of symbols are exactly the same. And so the only thing that distinguishes them is something that's much, much further on. And as you can imagine, having lots of look ahead complicates the implementation of lexical analysis. And so one of the goals in the design of lexical systems is to minimize the amount of look ahead or bound the amount of look ahead that is required.
So you might wonder why Fortran has this funny rule about whitespace. It turns out that on punch card machines it was easy to add extra blanks by accident, and as a result they added this rule to the language so that punch card operators wouldn't have to redo their work all the time. Fortunately today we don't enter our programs anymore on punch cards. But this example does help us understand better what we're trying to do in lexical analysis. So as I said, the goal is to partition the string. We're trying to divide the string up into the logical units of the language. And this is implemented by reading left to right. So we're doing a left to right scan over the input, recognizing one token at a time. And because of that, look ahead may be required to decide where one token ends and the next token begins. And again, I want to stress that look ahead is always needed, but we would like to minimize the amount of look ahead. And in fact, we'd like to bound it to some constant. Because that will simplify the implementation of Lexical Analyzer quite a bit. Now, just to illustrate that look ahead is something that we always have to worry about, let's consider this example, which we've looked at before, and just notice that when we're reading left to right, let's look at this keyword else here, when we've read the E, we have to decide, is that a variable name or some symbol by itself, or do we want to consider it together with the symbols that follow it. And so there's a look-ahead issue here. After we've scanned E, we have to decide, does that sit by itself, or is it part of a larger lexical unit? And there are single-character variable names in this example, like I, J, and Z. And so it's not unreasonable that E could also be one. And another example is this double equals. When we've read a single equal sign, how do we decide whether that's a single equals, like these other assignments, or that it's really a double equals? Well, in order to do that, if our focus point is right here, we have to look ahead and see that there's another equals coming up, and that's how we know, or how we will know, that we want to combine the two into a single symbol instead of considering this equals by itself. Now, another example from a language from long ago. PL1 is an interesting language. It was designed by IBM, and it stands for Programming Language 1. All right, it was designed to be the programming language, at least within IBM, that would be used by everybody, and it was supposed to encompass all the features that any programmer would ever need. And as such, it was supposed to be very, very general and have very few restrictions. And so one of the features of PL1 is that keywords are not reserved. So in PL1, you can use a keyword both as a keyword and also as a variable. So you can use keywords in other roles other than keywords. And that means you can write interesting sentences or interesting programs like this. And let me just read this out loud because it sounds interesting. If else, then equals else, else equals then. And the correct organization here, of course, is that this is a keyword, this is a keyword, and this is a keyword. And the other things, switch colors here, are all variables. These are all variable names. And as you can imagine, this makes lexical analysis somewhat difficult because when we're just scanning left to right, like when we're coming through here, when say we're at this point, how do we decide whether these things are going to be variable names or keywords without seeing what's going on in the rest of the expression? So lexical analysis in PL1 was quite challenging. So here's another example from PL1. Here we have a program fragment. We have the word declare, and then an open paren and a closed paren encompassing a bunch of arguments. I want to point out the balanced parens here, and then just a list of n things inside the parens. And it turns out that depending on the larger context in which this whole expression sits, this could be either a keyword or it could be an array reference. Now, I mean declare here could either be a keyword or it could be the name of an array, and these could be the indices to the array. And as it happens, there is no way, looking at just this much, that we can decide. This fragment is a valid declaration, and it's also a valid array reference. So it would depend on what came next. It might depend on, for example, whether there was an equal sign here, in which case this would be interpreted as an assignment, and declare would be the name of an array. And The interesting thing about this example is that because the number of arguments in here is unbounded, there could be n of them for any n, this requires unbounded look-ahead. Okay, so to implement this properly, as you're scanning left to right, to decide whether declare, again, is a keyword or an array reference, we would have to scan beyond this entire argument list to see what came next. Fortran and PL1 were designed in the 1950s and 1960s, respectively. And those experiences taught us a lot about what not to do in the lexical design of programming languages. So things are a lot better today, but the problems have not gone away completely, and I'll use an example from C++ to illustrate this. So here is an example of C++ template syntax, which you may be familiar with, or you may have seen the similar syntax in Java. And C++ has another operator called stream input. So this operator here reads from an input stream and stores the result in a variable. And the problem is here that there's a conflict with nested templates. So for example, if I have a template operation that looks like this, okay, notice what happens here. So my intention here is to have a nested application of templates, but I wind up with two greater than signs together at the end, and this looks just like the stream operator. And the question is, what should the lexical analyzer do? Should it interpret this as two closed brackets for templates, or should it interpret it as a two greater than signs stuck together as a stream operator? And it turns out that for a very long time, I think most C++ compilers have now fixed this, the C++ compiler in this situation would regard this as a stream operator, and you would get a syntax error. And what do you think the solution was? It turns out that the only fix that you could really do to make this lexically analyze the correct way was to insert a blank. So you would have to write this, and you would have to remember to put the blank in there so that the two greater than signs were not together. And you know, that's kind of ugly that we have to put in white space to fix the lexical analysis of the program. So to summarize, the goal of lexical analysis is to partition the input stream into lexemes. Okay, so we're going to drop down dividing lines in the string to decide where the lexemes lie. And we want to identify the token of each lexeme. And exactly because we're doing a left to right scan, sometimes we have to have look ahead. Sometimes we have to peek ahead in the input stream to figure out what the current string we're looking at, or the current substring we're looking at, what role it plays in the language.